Hi everybody, my name is John Handler. I'm a solutions architect with AWS, and I am a search specialist for AWS. I focus on our Amazon Elasticsearch service and our Cloud Search product. Today we're going to talk about Dynamo and Amazon Elasticsearch service. We have a lot of customers that we see who are using Dynamo and come to a point where they need perhaps a little bit more in terms of search capabilities. So they turn to Elasticsearch to figure out or to provide that additional search over their Dynamo data. So we're going to dig into Amazon Elasticsearch service primarily and explore it to see the kinds of searching that it affords, as well as how to link it up with Dynamo and get your data across and searchable. We're going to start with perhaps a overly general philosophical point, but I will put the question to you. What is a database? So the average developer would sort of say, well, you know, that's a place where I can stick my stuff and my application can then go and find that stuff and I can use it to create front ends and other application content to display to my end users. But, you know, databases do have some commonalities, and databases also have some very serious differences. And just to draw an analogy, you know, all vehicles, somebody's going to call me out on this, but all vehicles have wheels, right? But no one would say that, for instance, an 18-wheeler serves the same function or purpose that a big earth mover does. In those cases, you know, those two vehicles are designed for different tasks and they provide different functions and features to support the design that they were intended for, right? So if we look at the delivery truck, the Amazon Fresh truck, you'll notice it's got a door on both sides down close to the ground so that the driver can easily come out and deliver packages to where that driver is going. So in a very similar way, you know, databases can look very similar. They can look like, okay, that's just a place I'm going to drop my stuff. But your selection of a database implies a selection of a certain set of features and affordances that that database has for your data. And if we dig in a little bit and look at kind of DynamoDB and Elasticsearch service, by the way, it may be a little bit surprising to you, but Elasticsearch counts as a database, even though it's fundamentally providing search. It is in the databases world because it does have that kind of commonality of pushing data into it and then using it to support queries and sending that data back to end users. But if we look at DynamoDB and sort of feel out where does it specialize, DynamoDB, number one, is a durable storage solution. So, you know, data in Dynamo is triple replicated. It's a very durable store. And for that reason, it provides a good system of record. If you can push all your data in there, you have a reasonable expectation that that data will not disappear. Second thing, Dynamo is designed for high throughput at reliable latencies. So Dynamo is frequently used for high velocity data, things like clicks or scores or ranking. These are things that at high velocity, Dynamo has the capacity to handle that kind of turnover. And finally, Dynamo is designed to scale nearly infinitely and more or less hands-off. You just push your data in and you don't, for the most part, worry about it. Now, Elasticsearch service has a different set of capabilities. Primary among them, Elasticsearch provides you the means of indexing field data in all of your fields. So in contrast, Dynamo provides you with some global and local indexing capabilities, but they are limited in terms of how many indexes you can build. With Elasticsearch service and as a search engine, Elasticsearch provides you the means of indexing all of your data and making it the target for potential searches. In addition, Elasticsearch and as a search engine is designed and built to handle natural language. So when I have big blocks of unstructured text and I want to provide search across all of that text, I send it to Elasticsearch. Elasticsearch has capabilities in breaking that text up into individual words and processing them in a way that makes them a good target for matching. and we'll get into details about that. In contrast to other databases, Elasticsearch has a native notion of relevance. So many databases, most databases, are designed to allow you to pull large data sets out. You get all of the data back for your queries. Elasticsearch, in contrast, and again, search engines are designed really to provide you the best answers for your queries. If you think about your interaction with a search engine, you don't need to know all 100 million web pages that match. You want to know the right web page. That notion of relevance is built into the search engine. Elasticsearch can handle numeric values, things like dates and integers and floats, geopoints, all of those things. It has native handling for that allow you to both query directly for an exact value as well as perform range kind of searches across those values. And finally, Elasticsearch provides you features, a feature called Aggregations that allows you to summarize the values of fields across some search result. Aggregations are an extension of a feature that in older times we called faceting. Faceting, again, just does strict counts. Aggregations actually provide the basis not only for computing counts of values, but also for doing analysis. And we'll see examples of all of these different features, and we'll bring out in detail how they work and what you can do with them. So as we look at Elasticsearch and how does Elasticsearch work, it does work much like a database. I take my data and number one, send it as JSON into Elasticsearch service. Now we have two main use cases with Elasticsearch that we see for our customers. The first of those is a logging use case. For the logging use case, I have server logs, application logs, network logs, AWS service logs, all kinds of logs. Basically, if you're doing IT today, you have logs somewhere. And Elasticsearch, through its aggregations feature, provides a good way for summarizing and building visualizations on top of that data. That's the larger use case that we see with the service, and we're not going to cover that one today. The second use case is a search use case, and of course Elasticsearch is a search engine. So we see all kinds of application data that customers are sending to Elasticsearch for searching. Things like curated document sets or e-commerce products, et cetera, et cetera. All of that application data serves as a target for your customers to be able to find and, if that's the kind of application you have, purchase the items that they want. Now on the other end, we send queries to Elasticsearch via the Elasticsearch REST API. It's a rich API that supports a number of different features, things like direct matching, as well as Boolean combinations of different clause searches, supports metadata search, natural language search, and includes this notion of relevance, scoring, and sorting. Amazon Elasticsearch Service is a fully managed service that makes it easy to deploy and manage and scale Elasticsearch in the AWS cloud. We brought out this service in 2015, and mostly in response to the popularity of Elasticsearch and wanting to provide additional benefits that would make it easier to use Elasticsearch. So, the first important design constraint for us is that Elasticsearch service provides you with a drop-in replacement for an existing Elasticsearch deployment. It's compatible with the open source APIs, and it allows you to use it as you have been using it. But we make it simpler to deploy Elasticsearch clusters. So we have API calls that allow you to deploy or scale up or down an Elasticsearch cluster in the AWS cloud. We also provide features that make it simple to accomplish common tasks, things like securing your data. We have a number of different security features that make it simple to harden your Elasticsearch cluster and make sure that your data is encrypted and within your VPC to provide, again, that hardening of the Elasticsearch cluster. And we have a number of integrations with other AWS services that makes it simpler to monitor what's going on with your cluster. We integrate with CloudWatch to expose metrics about the cluster, and simpler to get data into your Elasticsearch cluster. We have integrations with Kinesis Data Firehose and with CloudWatch Logs and others that make getting data in much simpler. So having talked a little bit about Dynamo and Elasticsearch service, let's look in context about how we would expect to use them. So if we have a strawman architecture here, we have some application that has a distribution layer and perhaps a rendering layer that sends data out to EC2, from EC2, sorry, to CloudFront. We then have a middle tier with business logic, again, potentially on EC2. There are a number of different ways we could do this. Again, it's just a straw man. And then we have our data layer. And generally speaking, data flows vertically from top to bottom. Again, it's a straw man, so bear with me here. We frequently see one of the Amazon RDS databases, either Postgres or MySQL, as being the gold standard source of data. Then we see DynamoDB used commonly, again, for higher velocity data, things like inventory or clicks or ratings or locations. And then all of that data is flowing into Elasticsearch service, where Elasticsearch service is providing the search layer for the end user to get to the data that they want. So let's talk through an example and how to search your Dynamo table. And in this example, we're going to imagine that we are running or building a video streaming service, and we want to support our customers searching for movies within that context, and so that they can purchase those movies for streaming. And as we think about it, let's think about the design of the DynamoDB table. For those of you not familiar with Dynamo, here is a very, very quick and brief and sort of sketchy overview. Like all databases, DynamoDB works with tables. Now, a table has a set of items. These are kind of like rows. You can think of them that way. And each item has a set of attributes. Attributes are named values within that row. The attributes do not have to be congruent between the different items. As you can see, we have different numbers of attributes for the different items in the table. Most of the time, we think of DynamoDB items as being bag of values. Now, within the table, we have one of the attributes that is a partition key, and that partition key in some ways defines a bucket. So the partition key allows me to specify how to divide my data into different buckets of subdata. And this is in some ways, you can also think of this as a key value kind of access pattern. So the partition key provides the key, and then the rest of the attributes are the potential values. We optionally can also specify a sort key, and this allows us to provide multiple entries for single partition keys. So an example here would be a customer ID, and then that customer has some set of orders, and each order then is an item in the table. The sort keys do also allow us to do some searching and ordering across the data in the DynamoDB table. They allow us to iterate over keys and figure out what's in those buckets and bring those results. So in our movies example, we're going to use movies as items in our DynamoDB table. And the key concept here is that each movie has a particular breakdown, a particular set of fields that contain data about that movie. So in this case, we have a title, we have a year, we have description, we have actors and directors and writers. All of those can be attributes in our element in our DynamoDB table. When we define the table, really we just are going to specify the read and write capacity, which we haven't talked about, but this is necessary for us to tell Dynamo how many items we expect to read and write. And then we define the ID as being our primary key here. We also enable DynamoDB streams, which we'll come to in a moment. Within the individual items, then we have a schema for the different types of the items. It's all pretty straightforward. Our ID is a string, our title is a string, our year is a number, rating number. There's a couple of string sets, so where we have multiple items, things like actors and directors and genres, those are string sets. So that's how we're going to get our data into and structured in DynamoDB. Now let's talk about Elasticsearch Service. So when you use Amazon Elasticsearch Service, you create what we call a domain. A domain is a collection of hardware comprising data nodes and master nodes, and then also with software deployed onto it, most notably Elasticsearch itself, and exposed to you via an endpoint, which is a DNS entry. You send Elasticsearch API calls to that endpoint, and they are sent on to the cluster, and the cluster processes them and returns results. Much like DynamoDB works with tables, Elasticsearch Service works with indexes. You can think of that as a fairly reasonable analogy. An index is like a table in DynamoDB. It does break down in some of the finer points, but high level, that is how we structure data in Elasticsearch Service. Now, the index then contains a set of documents. The documents here are the entities. These will be the movies that we're going to import, and they are going to comprise basically the core entity, the target for search. Each document then contains a set of fields, and the fields are the name value pairs for the particular movie itself. So again, making the analogy, index is like table, and document is like item, and field is like attribute. So carrying that forward and how we expect to store the data in Elasticsearch Service, again, we have movies then are the documents in Elasticsearch Service. And similarly, we have a set of fields that contain values, things like the title, again, and the actor, director, stars, etc. And if we can look at the different types that Elasticsearch offers, and they control how the data itself is indexed. So if I have a text type field, then I am using that to index all of the words individually in that field. Something like a plot or description, I want to break that down so that individual words within that plot can match. And Elasticsearch, when I specify a text field, applies a full language processing across 34 different possible languages to provide the targets for search. The keywords are similarly a string type, but they do provide an exact match, right? So when I have metadata, things like the title, sometimes I would want to match as a full title. I might put that as a keyword. The genres, a lot of times if it's a UI element that I'm going to send as a string generated from my UI, I would make that a keyword type field. Those are the kinds of things that I would put in there. For the integer types, again, those will be indexed as numerics. They support exact matches as well as ranges and calculation on them. Dates, like other numerics, do support exact matching as well as date math. And then we have our geotypes, geopoint, geoshape. I can do bounding box searches. I can do geopolygons, and that allows me to match those. So that's how we'll get our data into Elasticsearch, well, into Dynamo and then into Elasticsearch and make it searchable. That's the underlying structure of things. So how do I get my data across? What's my normal way for loading data into Elasticsearch Service and making sure that it remains in sync with DynamoDB? So there's two basic phases here. I have a bootstrap step and I have a synchronization step. And I might or might not already have my data in DynamoDB. If I don't, then if I already have it in Dynamo, then I need to use an EC2 instance or similar to do a table scan and pull out the items one by one, construct the JSON for Elasticsearch, and then send that data to Elasticsearch service. If it's not already in Dynamo, though, I can hook up Dynamo streams, and then as I send my data to Dynamo, that stream will reflect all of the new items that I'm sending into my Dynamo table, and I can forward that to Elasticsearch service with Lambda. It's not a bad way to go, and especially because when we look at synchronization, Amazon DynamoDB streams receive items for it's controllable, but the stream itself will receive an item for each of the changes you make to your Dynamo table. So I use Dynamo streams along with Lambda to send that data to Elasticsearch service, and as I make updates, that data is automatically pushed to Elasticsearch service. Okay, so now we've got our Dynamo table populated, schema, got movies in it. We bootstrapped that data into Elasticsearch service, and we're synchronizing our updates via Dynamo streams and Lambda. And now let's explore some of the search features of Amazon Elasticsearch service. So we've already highlighted this, but the search engine sits between the user and the data that user is looking for. And the pattern here is that documents go in. Those documents are indexed. During that indexing process, each of the fields is analyzed according to the mapping, and the data itself is decomposed in whatever way is appropriate for that data type. And that data is then indexed. Now, Elasticsearch service creates an index for each field. So this index is both a high-level structure, and then there is a per-field index that we'll refer to as well. When a query comes in, we similarly analyze the query according to the fields that it's referencing. If I'm searching for the Iron Man in the title of the movie, and the title field has been analyzed as a text field along with English language, and we'll see all of the details, then I have to make sure that my query matches that field, right? So I analyze the query text the same way that I analyzed the text that I indexed. Then the query is going to pull from the index the matching results, score them, and send them back. So with Elasticsearch, you have a query API language called the query DSL. That allows me to specify searches in a rich array of ways. Fundamentally, it is a JSON API, and I use the HTTP GET against my index, and I use the search API call. You can see here an example of a simple query. In this case, I'm looking for the words Iron Man in the title field. The search results also come back, and those are also in JSON. There are two main pieces of the search results. At the top, we have a bit of metadata over here that tells me that the query didn't time out, tells me how many of the shards responded to my query, and did any skip, or were any skipped, or did they fail. So that's just metadata, and how long it took. So that's just some metadata. And then we have the sort of meat of the results, which is the set of hits. These are, for my particular movie, these are the movies or the documents that matched my query, right? So Iron Man, you can see here, is at the top. You can also see that we are able to retrieve from Elasticsearch, in this case, the full document that we sent in and indexed. So one of the key differentiators that Elasticsearch has with respect to DynamoDB is that Elasticsearch creates an index across every single field in the document in order to support low latency, high throughput search on all of the fields of a document. So if we look at that, on the left we have our document. Our document is JSON, but represented here as a set of fields. Fields are name value pairs. The example here would be title, year, actors, rating, et cetera, et cetera. So each of those fields then has a particular value. For our movie, title, Iron Man, right? We pass those values through an analyzer that's going to pull out the indexed terms from that value. So, and then we put all of those values into an index. This is called the inverted index. This is a core search engine data structure. And it's called inverted index because it goes from term to document, which is kind of the normal way to do it. But in this case, we have the term iron refers to a particular movie ID. The term man refers to a different movie ID. Both of those are in my field index. And then the term iron in my field index points to a list of all of the documents that contain the term iron. So this is the indexing, and this works the same for all of the textual data. It's similar for the numeric data, etc. When I want to query that data then, let's imagine I have title iron, title man. I first analyze that data. As I said, it has to be analyzed in the same way that the base data was analyzed. And I go to my indexes and I find those terms, iron and man. Then I pull the posting lists. So the first list would be the set of all documents that contain the term iron. The second list would be the set of all documents that contain the term man. I apply the logic of the query to produce a set, either union, intersection, negation, what have you, of all of the documents that match the query's terms and logic, right? So if I want to search for iron and man, then I do a set intersection on my posting lists, and I get a set of documents that contain iron and man. I then score and sort all of those documents to generate a result, which is the full sorted result of my query. So because we have all of our fields indexed, it's interesting to be able to create complex combinations of different field queries. And the bool query in Elasticsearch allows us to do that. First of all, we have a filter portion, which allows me and employs internal caching to make a faster match and retrieval, but the filter portion does not affect the scoring. Then I have various must not, or should. So I can say particular fields must be this. The field title must be iron. The field title must be man, etc. I also can exclude things with must not. And I also have the ability to send a set of clauses, at least n of which should match for the document to match. So here's an example of a compound Boolean query across multiple different fields. In this case, we have a query where the genre must be sci-fi. Gwyneth Paltrow must be one of the actors. We were looking for something less than $20. It has to be longer than 6,000 seconds and must be released before January 1st, 2000. Now we've also included a should clause here. In this case, matches that contain Mickey Rourke or Robert Downey Jr. will score higher based on Mickey Rourke and Robert Downey Jr. being in the actors field. As I've alluded to, Elasticsearch has native language capabilities for 34 different languages. We've talked about analysis a lot. When we look at text analysis specifically, then we have some input text that comes in. We have analyzers that are applied to it. They're both built-in analyzers and in some cases custom analyzers. And then we have the search data coming out. So looking at text analysis specifically, a number of things happen. So the first of them, and again, we're talking about here applying analysis to a block of unstructured text. The first thing that we do is we tokenize. There are lots of different tokenizers built in, and there are language-specific tokenizers built in. But for English, and in this case, a whitespace tokenizer works fine. Whitespace, again, separates each of the words based on the whitespace. You can see on the right that we have a stream of tokens that comes out from this tokenizer. The second thing we do in text fields normally is we lowercase them. This is because fundamentally we don't care what the capitalization is for these particular fields. The word wealthy should match the word wealthy whether or not it has a capital letter, same thing for when. Tony Stark here is an interesting question. Do we really want to match both capital T Tony and lowercase t Tony? We have other ways that we can handle that. In this case, because this is kind of, you want this to serve as a target for all queries, then we're going to keep downcasing with Tony and Stark. We remove common words that are of low value in terms of matching. These are called stop words. Some examples are a, and, is, and to. So again, these words probably occur in every single document that I have in my index. In that sense, they don't really provide me any value for determining whether a particular document matches a particular query. So it's better just to remove them. And that's what stop words do. You can see here you can set the set of stop words. It doesn't always have to be this set. You can add your own. A final thing that we do is we apply stemming. Stemming, much like downcasing, broadens the match possibilities for a particular document by taking the terms and making them, reducing them to a common stem and essentially creating equivalence classes out of all of the words that are stemmed to the same term. The example here, an example is runs, running, runner. All of those have a core concept run, hopefully, and in this case, represented by the stem of those words, which is run, right? So the stemmer is designed to take the words in English and reduce them to their common stems. You can see on the right, it's not always exactly clear what it's doing. The stemmer is, developed against many different corpuses of documents, and so it doesn't always make sense, but it does work to provide better matching. And we can see here an example of a text query. I have a query for steel in the plot, and I'm just showing the plots that come out. And you can see, steel is in all caps, but we're matching lowercase things. We also are matching steel and stealing in different search results. So this is all of our text analysis at work. Another key differentiator is Elasticsearch's ability to handle numerics like geopoints. So we can store geopoints, we can store hashes, we can store polygons, we can store complex geometric shapes, generally in support of my ability to query for items that are near me. So this is a search near me kind of feature support. And as you can see here, we can filter based on a bounding box. We can sort based on the distance to a particular location. And we can do all of that within Elasticsearch itself. Another key differentiator is that, as I mentioned, Elasticsearch service and search engines tend to incorporate a notion of scoring and sorting for all queries. You don't get everything out of a search engine. That's not a usual pattern. Usually you're looking for the best thing. So this is a somewhat complicated looking slide, but it's not that bad. We generally use a scoring function called Okapi BM25, which is also known as TF-IDF. And the idea here is a particular document retrieved for a query receives a score that's based on the set of matching terms summed across how many times or multiplied by how many times they match. So each term receives some score. If I'm searching for iron, the term iron then gets a score. And if it appears 16 times in a document, then I take the term score and multiply by 16. I sum all that up over all the query terms, and that is the score for that particular document. There are lots and lots of specializations and customizations that you can do on top of that basic understanding. In particular, you can add function scores that change the ranking. You can incorporate different values from the document. You might want to scale your score based on the rating of that particular movie, etc. So let's look at some results here for querying Iron Man. I have here a number of different results that come back. So there's an ID for each of these movies, The Sessions, Iron Man 2, Outlander, and Braveheart. And you can see the scores that we retrieve for those documents. Why is it that we're seeing Outlander, Braveheart, and The Sessions? Well, those actually have, we're searching here across the plot. So what we're looking at is the titles, but what we're searching against is the plot. The Sessions, Outlander, and Braveheart contain the terms Iron Man in their descriptions more than the Iron Man movies themselves. This is not the way we would usually search. Usually we would match against the title first and then the plot. So we can add, as I said, a number of different ways of adjusting the score according to our particular application. So our base score here is TF-IDF, and here we're matching the plot in Iron Man. I can add an exponential decay function that looks at today's date and then scales the scores based on the distance of the release date of that movie from today. In other words, newer movies score higher. Then I can look at the rating to scale my score by the rating, right? So here I'm saying, well, highly rated movies are likely to be more relevant, so let's bump the score up for that. And finally, I can even write somewhat freeform scripts that use normal sort of algebraic syntax on document fields, or in this case, the score. Here I'm saying, just to show you the example, I want to scale the score by 0.5. There are different ways that these different function clauses interact, and I can set the different modalities for how I'm going to combine all of these things into a single score. And then ultimately, I come out with a different ranking. And you'll see my score here is much different than it was on the prior slide that did not include my functions. The last feature that we'll dive into is called aggregations. So aggregations provide me the ability to sum up across different field values within a search result. So here's an example, and this is to support a feature called faceted drill down. You've used this feature before. In the left rail, usually of some kind of e-commerce site, you'll have a list of brands and sizes and colors and other facets of the search results. And you'll have counts there that say, 5,700 of these are Nike, 2,400 are Tommy Hilfiger, what have you. So the way we support that in Elasticsearch is through aggregations. I give my aggregation a name here, rating, and then I say I want to look at the rating field and create buckets from 7 to 8 and 8+. And then Elasticsearch computes for me the search results that fit into those different buckets and provides me back a result that tells me, in this case, 7 to 8, I have 27, and 8 and up, I have 6. Let's look at that in context of our movies. So in this case, I'm looking at matching everything. So my query here could dig in a little bit more specifically, but I'm matching every movie, and then I'm aggregating across the actors. So just that portion gives me a set of buckets where each bucket contains one actor. In our result here, you can see I have Robert De Niro, Nicolas Cage, Bruce Willis, etc. Now, a cool thing about aggregations is that you can nest them. So within each actor then, I compute the average rating for all of the movies for that actor, right? What goes into the bucket is the set of movies that actor stars in or is mentioned in. And then I take that bucket and I compute across that the average of the rating field. So Robert De Niro on top was 6.95, and then Nicolas Cage, and then Bruce Willis, etc. And note that they're not sorted by score. In this case, they're actually sorted by the actor name. So let's wrap up and talk about the ground that we've covered. As I said, we have a number of customers that use Amazon DynamoDB. to store high-velocity data or to store as a system of record for their application data. Dynamo itself is, designed for durable storage and high throughput at reliable latencies, which can scale nearly infinitely. Dynamo is nicely complemented by Elasticsearch service, where Elasticsearch service provides you the means of expanding the coverage of your search, of the ability to search the data. So we have an inverted index for every field. It also natively handles natural language, allowing you to perform searches across full text blocks in a way that respects the language. It has a notion of relevance and ranking. It handles numerics like dates and geo. And you can build aggregations either to look at statistics about your data set or to analyze features of your data set. Thank you very much for your time and attention. Really appreciate it. Have a great day.